podcast. Today we're at 3, modeling GIG, modeling with polynomial functions and data. The student works 1, 2, and 3. Let's take a look at the next page. Getting started. Release your regression. Recall the regression equation is a function that models a relationship between two variables in a scatter plot. The regression equation can be used to make predictions about future events. Any degree polynomial can model a scatter plot, but data generally has one curve that best fits the data. You may also recall that the coefficient of determination, R squared, measures the strength of the relationship between the original data and the regression equation. The value ranged from 0 to 1, with the value of 1 indicating a perfect fit between the regression equation and the original data. The teacher works 1A and the student works 1B. Number 1, sketch the given polynomial, then draw 10 data points on each coordinate plane, such that the given polynomial will model the data with a coefficient of determination close to but not equal to 1. Write the equation for the function and then use technology to determine the regression equation and R squared for the data. All right, let's go ahead and use our regression feature of Desmos. So we're going to go to Graphing Calculator, add table. All right, and let's plug the values in. Be careful as you're putting your values in. It's very easy to make a mistake, and you want to always double check that your values are put in correctly. All right, now we have our values in. We're going to use the quadratic regression. So all right, and we're going to round for the equation 1 decimal place. So now for the R squared value, it's common practice to round to 2 decimal places. All right. So there's your regression equation and your R squared value. Go ahead and complete 1B on your own. All right, let's take a look at the next page. Activity 3.1, applying a polynomial regression. City planners consider building a new stadium on several acres of land close to the downtown of a large city. They monitored the number of vehicles entering and exiting downtown from a major highway between 1 p.m. and 7 p.m. to determine current traffic conditions. 1. Analyze the table of values that represents the average number of vehicles entering and exiting downtown during the given hours of a typical workday. The value of time represents the start time for the full hour over which the vehicles were monitored. 1A. Describe any patterns you notice. Explain the patterns in the context of this problem situation. The number of vehicles increased to reach a maximum at 5 p.m. and then decrease again. This pattern makes sense in the context of this problem because rush hour occurs at 5 p.m. Well, let's take a look at the next page. Two, create a scatterplot of the data. Be sure to label your axis. All right, so we have our time labeled by 1, 2, 3, and so on to 8. And then here, the number of vehicles. Now, the number of vehicles by 1,000. So they're in thousands. Okay, So that's 2,000, 4,000, 6,000, 8,000, 10,000, 12,000, 14,000, 16,000, 18,000, 20,000, 22,000, 24,000. Okay, so let's go ahead and plot our points. So 1, 7's right here. 2, 10.8 is about right here. Some of the points you're going to have to approximate. 3 is 14.5, which is about right there. 4 is 21.1, which is about right here. 5 is 23.9, which is right here, or about right there. And then 6 is 19, which is about right here. And then 7 is 10. All right, go ahead and complete your scatter plot. All right, let's take a look at 3. Use technology to determine the regression equation for the average number of vehicles entering and exiting downtown. On a typical weekday, sketch the regression equation on the coordinate plane in question 2. How well does the regression equation model the data? Was the prediction about the type of polynomial that best fit the data correct? All right, so we're going to remove our previous regression. And before we do this, we need to adjust our window to match the one on the paper. So we're going to go from 0 to 8 and 0 to 24. Okay. And let's go and add our table. Okay, we need to zoom out the window just a hair. And then let's go into quadratic first. So all right, let's go and round to 1 decimal place. Now for the r squared value, it's common practice to round to 2 decimal places. So okay, so there's your quadratic regression and your r squared value. Now let's go and take a look at the cubic. So exit that, and then all right, and let's go and round to 1 decimal place for the equation. And again, for the r squared value, it's common practice to round to 2 decimal places. So there's your equation. And you can see that 0.98 is a better r squared than 0.83. So the cubic regression y equals negative 0.4x cubed plus 3.5x squared minus 4.5x plus 8.4 is the best fit. All right, go ahead and finish that up. Let's take a look at the next page. All right, 4. Use a regression equation that best models the data to make predictions. Let's let x equals time. 4A, downtown is congested when there's more than 20,000 vehicles are on the street and on the highway. Predict when the downtown will be congested. Explain your reasoning. So we're going to go back to our equation, and we're going to graph y equals 20. That represents 20,000. And we can see that it's above 20,000 between here and here. Now, that's 3.85, so it's 3 o'clock, but 0.85, we need to find out the minutes. So we're going to go to Desmos. Let's go to Scientific Calculator. And we need to multiply 60 times 0.85. So we can see that that's 3:51 p.m. So the graph is above 20,000 vehicles for the time interval 3:51 p.m. to 6.017. So we need to convert that 0.017 to minutes. So that's 1 minute. So that would be 6:01 p.m. So downtown will be congested between 3:51 p.m. and 6:01 p.m. All right. 4B, predict the hours and the number of vehicles that enter and exit downtown is less than 20,000. Explain your reasoning. So same graph, same line, but now we're looking at when it's below. We have to start here. 0 represents 12 p.m., so it's below from 12 p.m. to 3:51 p.m. So 12 p.m. to 3:51 p.m. or 6:01 p.m. to 7.54. So we need to convert that 54 to minutes. So 7:32 p.m. So 6:01 p.m. to 7:32 p.m. So fewer than 20,000 vehicles are on the highway between 12 p.m. and 3:51 p.m. or between 6:01 p.m. and 7:32 p.m. Predict the number of vehicles that enter or exit downtown during the hour starting at noon. Noon, the x value of 0 represents noon, so we need to go back to our graph, and we're looking at right here. So noon, that's 8.443, but that's in thousands. So we need to come over here and multiply 8.443 times 1,000, which is 8,443. So 8,443 vehicles are on the highway at noon. All right, let's take a look at the next page. All right, we're going to go ahead and mark off this page. Activity 3.2, determining a best fit polynomial. Although the minimum wage may vary from state to state, the U.S. federal government sets an absolute minimum wage for the nation every few years. 1. Analyze the table of values that shows the absolute minimum wage and the years it was enacted by Congress. Predict the type of polynomial that best fits the data. Explain your reasoning. Now, this is time since 1950. So 5 would be 1955. 6 would be 1956. 11 would be 1961, and so on. Okay? All right, so let's take a look at the next page. Analyze the data graphically. Use technology to determine the best regression function f of x to model the changes in the minimum wage over the years since 1950. Sketch the regression equation in the coordinates plane. Be sure to label your axis. So here, this is years after 1950, and then this is dollars. Okay, so let's go ahead and graph our points. So 5.75 is about right here. 6 is 1. 11 is 1.15, so that's about right there. 13 is 1.25, so it's about right there. 17 is 1.4, so about right there. 18 is 1.6, so about right here. 24 is 2. 25 is 210, so about right there. And then 28 is 2.65, so about right here. 29 is 2.9. 30 is 3.10. 40 is 3.8. 41 is 4.25. 46 is 4.75. 47 is 5.15. 57 is 5.85. All right there. And then 58 is 6.55. So somewhere about there. And then 59 is 7.25. All right. Go and finish up the scatter plot. How well does regression function model the data? So let's go and take the regression equation. Now we need to remove our previous problem, and we need to adjust our window. In this case, this is from 0 to 60 and 0 to 7. Okay, and let's go and add our points. Now there's a lot of points, so it's important to double check to make sure you don't make a mistake. And if you do, make sure you correct it in the table. Let's go up to the top. And then all right, so we have our points. Now let's go and go to our regression. All right, now in this case, we're going to have to write every decimal place down. And then the R squared value, again, common practice to round to 2 decimal places. All right, so there's your equation. All right, now use the regression equation that best models the data to predict the minimum wage in each given year. So in 2020, to find that number that we're going to use, we take 2020 minus 1950, which is 70. And to find f of 70, we're going to plug 70 everywhere there is an x. Now, there's a good way to use Desmos to do this. So we're going to go to the scientific calculator, and we're going to do this. We're going to type in now you notice it's showing an error, but you'll notice something very cool in just a second. Now, it says an error, so we press enter. And then I'm going to tell Desmos that I want x equal to 70. And now you'll see that it calculated so that we're talking about money, so 2 decimal places, 8.33. So $8.33. Okay, so 1945, we need to take 1945 minus 1950, which is negative 5. So we can come back here, and all we have to do is change the x value to negative 5, and we get 0.53. So 53 cents an hour. Okay. All right, let's go and take a look at the next page. Number 4. Use a regression function to make a prediction about events in the distant past and distant future. Explain your reasoning. 4a. According to the regression equation, what was the minimum wage when the Civil War ended in 1865? So we need to take 1865 minus 1950. So let's go and do that. 1865 minus 1950. So that is negative 85. So that's the value we need to plug in. So we're going to change negative 5 to negative 85. And we see our value is $17.96. Okay, this does not make sense in terms of this context. 4b, do you think a cubic model is appropriate to predict the minimum wage in the distant past and future? A cubic model is inappropriate to predict the minimum wage in the distant past and future. All right, go ahead and mark this off. Finish up your notes and have a wonderful Wildcat